Abdoulaye.
Yes. Hey, Ben.
Great. Okay. So when we can host you in person,
Yeah.
whenever that can be, we would be at this point walking from our atrium where
Mhm.
we're eating cookies together and drinking coffee and tea, and we'd be working our way over to the atrium at this point. Actually, people would be piling in.
Let's imagine
We'll give
how
it
you would.
maybe another minute, and then we'll go ahead and start. I'll introduce you. Okay, so just send another link here.
Great. So
Okay, I think that's good. I think we'll go ahead and start. So it's my pleasure to virtually introduce Abdoulaye Ndao. Professor Ndao is at Boston University in the ECE department, Electrical and Computer Engineering. Um, he got his PhD at the University of Franche-Comté in Eastern France. I think I probably mispronounced that. And then he moved to do a postdoc at UCSD, and thereafter at Berkeley. And then before moving relatively recently to start as a new faculty at Boston University. So starting up as a new faculty is a challenge, even in the best of times. And we're talking about some of the challenges even during this time. Yet despite that, it sounds like we'll get to hear a lot of his results that he's managed to perform even during these difficult times. I looked at his faculty page. He's got a number of awards, including a prize winner of the Institute for Global Entrepreneurship at UCSD, and a few other innovation-related awards, especially related to topological lasers. So I think we might hear some of that today. So I'll leave it to you, Abdoulaye, if you want to entertain questions throughout the talk. There's this raise hand feature. It can be difficult to do over Zoom, but oftentimes there's a raise hand feature and unmute feature. I'll leave it to you if you want to wait to
You,
answer those at the end or
they
not.
can also stop me and just ask question directly. That's okay also.
Great,
Yeah,
great.
if they want to. Yeah.
Okay, well, without further ado,
Yes. Thank you for the invitation and thank you for all being here to listen my talk today. So my name is Abdoulaye Ndao, so new assistant professor at Boston University. So today I would like to talk about symmetry and topology in photonic nanostructure. So as we all know, in the recent years, the demand of miniaturization and integration is of a great interest, especially devices that we are using in our daily life, such as cell phone, GPS, and so on. And if you look at this new cell phone in a very tiny space, you can see that we have almost 10 functionality in the very tiny space. So in order to satisfy such high demand, new integrated optical devices must be compact, multifunction, multi-frequency band operation, and so on. And in this perspective, we propose and demonstrate for the first time a new type of laser that we call topological laser. What is interesting on this laser is the fact that this laser, it is one-way propagation, which means that you don't need, if you want to to pack them on chip, you don't need any additional component to avoid back scattering of the light like isolator. You can have an arbitrary shape, which means you don't need to have a specific space to integrate your device if you want to integrate a topological laser. The second part of the talk will be dedicated to what we call exceptional point. And I will show the demonstration of exceptional point in plasmonic system and how we can use such exceptional point to show or to detect attomolar concentration. And the last part of the talk will be dedicated to the first demonstration of an active bandwidth meta lens that can go from the visible to the IR with almost 70% efficiency. So I will begin my talk with, just move this. With the topology. So what is topological insulator? So imagine you have a topological insulator with given energy band, conduction band, valence band, and a band gap, and you to put free electrons within the band gap, they will not propagate in any direction. Basically, you are in gap region or insulating state. However, if you take free electrons that you put inside a bulk material and you apply a magnetic field, they will start to circulate in same direction with the same cyclotron frequency. In this case also, for given energy band, conduction band, valence band, and band gap, if you take free electron within the band gap, they will not propagate in any direction because of vector cancellation. But now, if you look at here, right at the boundary, you just if you look at here, right at the boundary, you can see some semicircle. What does this mean? This means that if you put free electrons right at the boundary and you apply magnetic field, they will start to propagate in forward direction without any back scattering of the light, regardless of the shape of the boundary. In this case, which are quite similar to the quantum Hall effect, we use external magnetic field or cyclotron effect. There is many other cases that can have the same effect but don't require to use any external magnetic field and are based on spin Hall effect rather than cyclotron effect. And in this case, when it is spin up, you have forward propagation, and spin down, you have backward propagation. All the story I just mentioned here are based on fermionic system, but it was demonstrated that under specific condition, under specific characteristics such as breaking time reversal symmetry, breaking spatial symmetry, or creating artificial gauge field, some of the fermionic system can be transferred to bosonic system like photons. This work was awarded recently in 2016 by a Nobel Prize for David Toules, Duncan Haldane, and Michael Kotzer. So now I would like to show some work that has been done in the literature trying to use topological insulator to demonstrate some devices from acoustic to microwave in terahertz or in optics, either using ring resonator or spiral structure to create artificial gauge field. So all this work I just mentioned here and many other work in the literature shows the robustness of the topological insulator. But now a fair question that we can ask, can we use such a topological insulator to make a real devices? In 2017, people tried to realize to use topology to make a 1D laser by using zigzag grating or using HSS model. But the question was how we can make such a structure in 2D or 3D dimensional structure. And in 2017, we proposed for the first time a topological laser that is made by a hybrid photonic crystal where we have a trivial and non-trivial photonic crystal. And right at the boundary, we have an edge state that emit light at 1.55, and we use the InGatsby as a gain material to have the laser. And later on, in 2018, another topological laser was demonstrated by using ring resonator. But again, in the context of miniaturization, the smaller that you have, the better will be. And if you compare the unit cell of the current of this new laser compared to the size of our laser is almost exactly the same, which means that our proposed laser can have the advantage to be in the integrated optical devices. And in our platform, we use magnetic material to break the time reversal symmetry. So how our platform looks like. So it is a hybrid photonic crystal made by two types of photonic crystal. We have the photonic crystal of the cavity is the air-hole-shaped photonic crystal with a triangle lattice, and it is designed to be a trivial photonic crystal. And the photonic crystal inside the cavity is the star-shaped photonic crystal with a square lattice, and it is designed to be non-trivial photonic crystal. And both photonic crystals are made in InGatsby and bonded in yttrium iron garnet as a magnetic material to break time reversal symmetry. So when we uniformly pump the whole structure without any with processing an external magnetic field, the edge state will be excited and will propagate and eventually couple to the waveguide, which just consists of removing one line of the trivial photonic crystal. So now in my next slide, I would like to show how such a design can be done. To design such a photonic crystal, what we first did is we consider the two photonic crystals separately. The first one is the air-hole-shaped photonic crystal with the triangle lattice, and we plot the band diagram of the structure and calculate the chain number of the mode below this band diagram when we apply magnetic field. And the calculated chain number will give a value of 0, which means that our photonic crystal is a trivial photonic crystal. And the second step consists of designing the photonic crystal of inside the cavity. And when we apply here a magnetic field, we have a very narrow band gap that is open, and we calculate the chain number of the mode below this band gap is equal to 1, which is non-zero, which means that we have a non-trivial photonic crystal. Since our goal is to work at 1.55, what we did is we choose the geometrical parameters of both photonic crystal in order to overlap them around 1.5. Overlap the two band gap of the photonic crystal and also at around 1.55. So now the next step is how to excite such photonic crystal and see if we can have the edge state. So what we did is we put the two photonic crystals next to each other, and right at the boundary we put a point source. And when we apply a magnetic field, the light will propagate in forward direction. And when we flip the sign, it should go to the backward propagation. And this shows that we successfully designed a photonic crystal that can have edge state, and the band gap of the two mode are of the mode are overlapping around 1.55, where we have the highest gain, and all the two photonic crystals are bonding in the yttrium iron garnet, which will be used to break the time reversal symmetry. So after successfully designing such a photonic crystal, the next step consists of the nanofabrication that I show the ACM image of the fabricated structure. And the fabrication is done in 3 different steps, which is e-beam lithography, etching, and bonding on magnetic material. So as seen here, the quality of the fabrication, you can clearly see we have the start shape of the photonic crystal inside the cavity, which is well defined, and the air-hole shape also, and we have here the boundary. We also add a waveguide, which will couple the light out, and this is what we will use to show if our system is lasing the collecting power output of this lenses fiber. So now how to characterize such a device. So what we first did is we uniformly pumped the whole structure without processing any external magnetic field. And as seen here, we don't have any edge state. And when we apply a magnetic field, we can clearly see that the edge state is very well defined. But the goal is not only to show that we have edge state, but it is also to show that the edge state that we have, it is the one that is lasing. To do that, what we did is we couple a lenses fiber at the edge of this waveguide and look at the photo emission as function of the point power. And as seen here, we can go from spontaneous emission to the lasing action, which shows that we successfully design, we fabricate, and we show we can have edge state, and the mode is lasing. But as I mentioned at the beginning, we want to show that the mode that is lasing here is self-isolated, which means it is only one-way propagation. So how we can prove that the edge state that we have is going in one can be one-way propagation? To do that, there is two methods. Either we couple two lenses fiber at the edge of the waveguide and look at the ratio between the two waveguide, or to only put a one fiber at the edge here and look and flip the sign of the magnetic field. We know that the first method experimentally will be very challenging to control the coupling coefficient at the both sides of the waveguide. So we choose the second method, which consists of having only one lenses fiber that we can control the coupling coefficient, and at the same time we just flip the sign of the magnetic field and we can see. And as seen here, when the magnetic field is going upward, we have lasing, and when we flip the sign, we don't have lasing, and the isolation that we have here is almost 10 dB. But what I mentioned at the beginning is it is also robust to any deformation of the shape. And in order to verify that, since we show it is lasing, it is unidirectional, and it is edge state, we change the shape of the photonic crystal. So before we have a square shape and we deform the shape of the square, and in the same way we did the design of the both photonic crystal, and we did the fabrication in the same way, and we look at with magnetic field, we can clearly see that we have edge state on both photonic crystal, and we look at the isolation in the same way that we did the characterization. And this clearly shows that we can have an isolation almost of 11 dB in both sides. So the design is successfully, we can show the edge state, we can show that we can have lasing with the edge state, which is self-isolated. It should propagate in forward direction without any backscattering of the light. So in order to prove that, we choose an arbitrary shape of the structure that we try randomly. And as seen here, we did the fabrication in the same way, and we look at without magnetic field, there is no edge state. And when we add a magnetic field, the edge state is very well defined, and we look at the isolation between the two by flipping the sign of the magnetic field, and we have 11 dB of isolation. So this shows that this topological laser is robust to deformation. We can shrink the shape without losing any functionalities. It is one-way propagation, and we can have an isolation almost of 11 dB. We did as a top 10 breakthrough physics world in 2017. So we show for the first time that we can design a geometrical independent cavities. We can shrink the chip without losing any functionalities. It is self-isolated, and this new type of laser can be used in different on-chip design or circuit for better functionalities. So this
Abdoulaye, the sound is a little bit intermittent.
as we all know,
I wonder if
my sound.
yeah, I wonder if you could. It was like about the last 30 seconds or so. Sorry, could you rewind?
He just this slide. Oh, what's going on?
It was the previous slide. We caught the story that it was
My
robust
Zoom
against deformation.
is freezing. Uh, I don't,
You could, yeah, that's a uh, good suggestion. You could try cutting off your video in case it's a bandwidth issue. If you turn off your camera, we can still see your screen and hear your voice, we hope. Oop. Here we go. Please come back in. All right. Adventures in Zoom.
everything.
Eh, All right. We can hear you now.
I'm back. Sorry,
No problem.
I don't know what's going on.
Yeah.
So I was here. It was cut off, or
Uh, we heard your conclusion that using this shape, I think this particular shape you're on a slide, showing that it's robust against deformations of the pattern.
okay. So I was just trying to list all the possibilities or all the functionalities that topological laser can give that I list here. That is
Yeah.
robust to like deformation. It is self-isolated and can be designed for complex functionalities or complex system.
Yeah.
So
That was it.
now I would like to go to the second part of the talk, which is exceptional point. So I would like to begin this part by comparing Hermitian and non-Hermitian system. So as we know, most of the physical systems are open in nature, which means that energy can flow in and out and exchange with the environment as absorption or radiation, which is in contrast with a closed system where energy stays conserved inside. One of the fundamental differences between Hermitian and non-Hermitian system is the fact that for Hermitian system, the eigenmodule do not decay and the corresponding eigenvalue are real. And for non-Hermitian system, the eigenmode do decay and consequently the corresponding eigenvalue are complex. So in the last decade, many people are trying to compare the physics of closed and open system. This renewed attention underline one of the fundamental difference between closed and open system, which is the singularities of Hermitian and non-Hermitian system. For a Hermitian system, mode coupled to induce singularities that we call dibolic point, where the eigenvalue are real. And for non-Hermitian system, mode will couple to induce two types of singularities, where we have exceptional point and dibolic point. And exceptional point have the eigenvalue are complex and the eigenvector skew. So now what I would like to show exactly is what is exceptional point. So exceptional point is the special properties of a non-Hermitian complex matrix that is at exceptional point is defective, and at exceptional point you have the eigenvalue and the eigenstate that coalesce. So now I would like to show how we can explain in the very easy way how we can reach such an exceptional point. Since it is a non-Hermitian system, I would like to consider a very simple 2 by 2 matrix of a non-Hermitian system and look at how they behave as function of the two physical parameters that can help to reach exceptional point. And to do that, I would like to consider two ring resonator and select the two physical parameters to reach exceptional point. And the two physical parameters here will be the radius of the resonator, which will determine the resonant frequency, and the distance between the two resonators, which will determine the coupling coefficient. Again, since it is non-Hermitian system, we can have the real part and the imaginary part as function of the two physical parameters and look at how they behave. So what we will do is we will calculate real part and imaginary part of the system as function of R and D, which is the radius of the resonator, which will give the resonant frequency, and D, which will be the coupling coefficient that will the distance between the two resonator that will give the coupling coefficient. So when we plot the real part as function of the two physical parameters, you have a very nice Riemann sheet where you have avoid crossing here in this side, and the other side you have crossing, and here in the imaginary part, you have the opposite. You have crossing and avoid crossing. And what is interesting here, if you look at very closely, there is only one single point where you have real part and imaginary part are exactly the same. This is the point that we call exceptional point. So how now such exceptional point can be used for different application in photonics? People are using it to demonstrate single mode lacing for chirality structure, non-reciprocal devices, or recently using it for gyroscopy because it is very sensitive to perturbation that I will come on to show why exceptional point is more sensitive than a normal sensor. So exceptional point also is done in acoustic, microwave, and in optics, either by using a waveguide where people use what we call parity time symmetry, where you have to engineer loss and gain to be able to reach exceptional point, to compensate between loss and gain to reach exceptional point. Now, the question that we can ask, why we don't have exceptional point at sub-wavelength scale? Because current method that people are using in optics is based on the combination of loss and gain, and it will be very challenging to control loss and gain at sub-wavelength scale. The second question is why we need sub-wavelength scale exceptional point. So to reply to this question, I would like to go to the next slide and compare exceptional points, the two singularities that I just mentioned before in the previous slide. The first singularities, which is dipole point, which is for Hermitian system, and the exceptional point, which is for non-Hermitian system. So one of the most striking character of exceptional point is when it is subject to perturbation. Here, we consider the perturbation as epsilon, which can be a refractive index change, which can be a concentration change. But here we consider that the value is epsilon, that we change from 0 to 1. And we look at how the resonant frequency changes as function of this perturbation. In blue, which is dipole point, is always linear to the perturbation. But when you have exceptional point, which is exceptional point of second order, which means you have just two mode, you have square root behavior. When you have exceptional point of third order, you have cubic root behavior. If you have exceptional point of n order, you will have n here, which means that depending of the order of the exceptional point that you will have, you will increase the sensitivity of your sensor or detector. So now I would like to respond to the previous question. We know that exceptional point can enhance the sensitivity of a device. We know also that plasmonic can concentrate or can confine light at sub-wavelength scale. So now what we want to do is to combine the enhancement of exceptional point and the confinement of light from plasmonic system to be able to detect a very small amount of concentration. So to do that, what we first do is we consider a system where we have an array of metal bars, and we look at how the hybridation of the two metal bar can increase or can bring new two different modes that we can engineer to reach exceptional point. We have two bars are exactly aligned. We have the electrical dipole. We have the symmetric mode, which is associated with the electric dipole, and the magnetic and the antisymmetric mode, which is associated with the magnetic dipole. and this is the two mode at opposite symmetry. So now the idea is to use this two mode at opposite symmetry to be able to reach exceptional point. How we do that? We know that when you pair two metal bars close to each other, you hybridize their plasmon wood in two different modes, where we have symmetric mode, which is more radiative and it is at the high frequency, and antisymmetric mode, less radiative, which is in the low frequency. As seen here, if you look at the quality factor, this is larger, which shows that this is more lossy than this one. But in this case, you have the two bars. There is no offset between them. As seen on the top right, the two bars are well aligned and they are not shifting between each other. So what we will do, we will start shifting one bar respect to the other one, as seen here. And you can clearly see that the symmetric mode will weaken to become, which have a repulsive character, will weaken to become attractive, and the attractive character of the antisymmetric mode will become to become the repulsive character of the antisymmetric mode will become to become attractive, and at some point the two resonant frequency of the two mode will cross. This is what we observe here. We change the dx from dx equal 0 to dx equal 80. You see the two mode will get closer. And when you go up to dx equal 140 nanometer, the two mode will cross. This is what we call the resonant crossing of the two mode, which correspond to the real paths that I showed before, that we should have a real path crossing and avoid crossing and vice versa. So this is what we have by changing dx from 0 to 200. 0 means that the two modes are well aligned. So you have in red the antisymmetric mode, which is more radiative and high frequency, and low frequency you have the symmetric mode. By keep changing dx, at some point you have the two resonance mode crossing. But what I mentioned at the beginning is, in order to reach exceptional point of second order, we need at least two physical parameters. So we identify first parameters that can have help to have a resonance crossing. But how about the second frequency, the second parameters? To do that, what we first do is we consider a just single layer and put a metal bar and see how it behaves as function of how the resonance frequency of the single metal is behaving as function of the geometrical parameters. So what we did here, we consider Py, which is the periodicity perpendicular to the length of the bar. And we look at, when we change the value of the Py, we see that the resonant frequency is decreasing as Py is increasing. And we have also the loss rate. It is also decreasing when the Py is increasing, which means that this parameter is very important because it's changing both the resonant frequency and the loss rate at the same time. So by combining Py and dx that I define as an offset between two bars, we should be able to reach exceptional point. So to do that, we first try, as I mentioned, we say we have two symmetric bars. The first parameter is the dx, the shift between the two bars. The second parameter, this is just the unit cell I show, will be the Py. But very surprisingly, when you change the dx and Py in this configuration, you can definitely have resonant crossing, but you will have always avoid crossing between the two modes, which is the symmetric mode and antisymmetric mode. So we said, oh, that's a good question, because the condition to have exceptional point was to have two physical parameters that can change the resonant frequency and loss rate at the same time. We have it, but we cannot reach exceptional point. What is the problem? The problem is the symmetric mode and the antisymmetric mode have very different loss rate, because this is very radiative mode and this is low radiative mode. And there is no way you can change the physical parameters to be able to have the two modes having the same loss. So we say now what we can do to make it happen is to make this symmetric and antisymmetric mode to be no longer a pure symmetric mode or pure antisymmetric mode. We have to make them hybrid mode. To do that, we have to break the symmetry of the structure. and there is different way to break the symmetry. The first method that we propose to break the symmetry is decreasing the length of one bars compared to the other one. And in this case, by changing the two parameters, we can really have avoid crossing in the resonant frequency and crossing here. And in the middle, you have exceptional point, which is the opposite in the loss rate, where we have crossing and avoid crossing. So this shows that we can successfully show the existence of exceptional point is the plasmonic system. But the goal was not to show just the existence of the exceptional point. The goal was to use exceptional point that can enhance the sensitivity and the plasmonic system that can localize field at sub-wavelength scale. But in this configuration, where you have the bar is embedded on a dielectric, the hotspot will not be in contact with anything that you want to sense. So now we have to have an alternative solution that can make exceptional point at the same time be able to do something. To do that, we propose another one, which consists of having the two bars have the same size, but one is embedded in a dielectric, which is SU8, and the refractive index is 1.58. And if you compare these two bars, the lengths of the two bars are as if are different because the effective medium are different, which is the same as decreasing one bar compared to the other one in the same medium. And we look at here that in resonant frequency, we have avoid crossing and crossing, and we have the opposite in loss rate, which shows that we have successfully designed an exceptional point that can be used as a sensor because this configuration is realistic. So the second, since we show that we are at exceptional point, I mentioned when I was comparing diabolic point to exceptional point,
Oh, the audio is cut out again.
can you hear me?
Now we can. It just popped back in.
Hello?
Hello. Can you hear us?
Hello?
Hello? Waving. We can hear you.
Hello.
Oh, okay.
Yeah.
So the second things that I was saying is in order to know that we are at exceptional point, we can compare them when there are having a perturbation that we call epsilon. And as seen here for diabolic point, we have always a linear change in the delta omega, and for exceptional point we have a square root behavior. We just add a cladding on top that we change the refractive index from 1 to 1.10 or 1.2, and we see that exceptional point is better than diabolic point and have a square root behavior.
Shoot. This is good stuff. It's cut out again.
But the something you should operate at the regime. Hello?
Hey, yeah, we're getting you in spots. I'm sorry. I wish we knew what was cutting out.
I cannot hear you, Ben. You asked something.
Okay. Here, I'll mute myself. Maybe you can hear.
You asked a question?
Mike, did you have a question?
Just said we could hear you, Ben.
Okay.
Can I go?
Yeah, I'll. How about this? When folks, when the audio cuts out, how about we use the reactions? There's an open mouth reaction that we can pop up. And then Abdoulaye, if you see that open mouth reaction on people's profiles, then that would indicate that your audio's gone.
I cannot hear you.
Well, the important thing is we can hear you. Let's see.
Chat feature.
Okay. Well,
Hello?
go ahead.
Can you hear me?
Yes.
Okay. So I was saying here that in order to prove the existence of the exceptional point, we just add a cladding layer on top and see if we can have this square root behavior again by changing the refractive index from 1 to 1.2. And as seen here, from 1 to 1.15, you always have this square root behavior where exceptional point is better than diabolic point. But after 115, diabolic point become more sensitive than the exceptional point, which means that if you want to use exceptional point for a sensor, you have to use a very small perturbation, which means that you have to operate in the regime where the perturbation is very small. And to prove the square root behavior, we plot just the log scale, and you have 1 over 2, which prove is this square root behavior, and 1, which is for the diabolic point. So this is the just to give an overview of the platform that we use. This is an array of a plasmonic metal bar sitting on top of SU8, and inside the SU8 we have another second bar where we control the two parameters, which is py, the periodicity in y direction, and dx. So in order to fabricate our structure, we use 3 main steps of fabrication. E-beam writing, we have liftoff and metal deposition and liftoff. And in order to verify the geometrical parameters of our structure, we use the FIB, and we make a cross section. And as seen here, the top bar and the bottom bar, the shift is very well respected, and we can also verify the geometrical parameters that we want to use. Now, the second step is how to prove experimentally that the exceptional point exists. If you want to prove it by using this Riemann sheet, it will be more complicated and require more data. So the best way is to do a cross section. We have in this side a crossing, here avoid crossing, and the
Okay, we've lost audio again. Rats.
I think we lost him completely. Not just
Yeah,
the audio.
we'll come back in. Let's see, I'll text him. There we go. One thing, Spencer, do you think if we made Abdoulaye co-host, do you think Zoom would dedicate more bandwidth or something?
share my slide. Could you make me host again?
Yes, let's see here.
Okay.
There we go.
So share screen. Did you hear me until here or no? I have to go back.
Let's see.
Yeah, you just started explaining that you're going to take a cut instead of trying to map out the whole surface. And
Okay, so yeah, we just take a cut here that we consider the py is smaller than the py of the exceptional point, and we look at what's going on in terms of experiment. We compare numerical simulation and experiment, and you can see here that in red we have omega A and omega B, the two modes are crossing, and we did the same cross in the line width where we will consider the py equal 400 and we have avoid crossing. And to prove that we have the opposite, avoid crossing and crossing, we consider also a py which is higher than the py of the exceptional point, which is 430, and we have avoid crossing here and crossing. This shows that we successfully designed a plasmonic exceptional point and experimentally demonstrated. So now, again, the goal was to use the exceptional point for sensing for a very low concentration. So what we did is we used the anti-IgG, which is the most common type of antibody in our blood circulation. So this is a flow chart how we functionalize the metal bar and look at how the exceptional point resonant frequency change as function of the concentration of the anti-IgG. So we start fully saturating the top of the bar using a linker. After that, we burn antibody bonding. This will be what will capture the anti-IgG mouse that we will use for different concentration. So what we did is we start with the very high concentration, which is very high compared to where exceptional point will be more sensitive than the diabolic point, which is at 1,500 attomolar, which is nothing as a concentration. And you can see the behavior. Diabolic point is more sensitive than exceptional point. But when you keep decreasing the concentration, the difference between diabolic point and exceptional point decrease. And at 1,000 attomolar, exceptional point become more sensitive than diabolic point, and the difference keep increasing, and until 50 to 30 attomolar, where we reach the linker limit. What is the meaning of we reach the linker limit is when we start doing the functionalization of the top bar, we fully saturate the top bar. And when you saturate the top bar, you have a delta shift. The resonant frequency will shift. And the shift induced by the linker is around 5 terahertz. So any concentration that you will add in the system that cannot bring like a shift more than 5 terahertz cannot be detected, which limit our sensor at 100 attomolar that we can detect. So we can consider this concentration as a perturbation also, and verify in different ways that first we are at exceptional point, that we have it experimentally, and it is more sensitive than the diabolic point before we fabricate the two structures in the same sequence. And for here, we show that we can detect like 15 × 10⁻⁹ nanogram, which is almost 300 times better than the state of the art in terms of concentration detection using a plasmonic system. So this will bring me to the second part of my talk, where we show for the first time that we can have exceptional point at sub-wavelength scale. And we can also enhance the immunoassay detection using EP with a record detection. So now I would like to go to the next part of my talk, which is the broadband meta lens. So I will start this talk by presenting one of the fundamental discovery of Newton, which consists of the decomposition of the white light source using a prism, as seen here in the picture in the schematic illustrating the experiment. Optical dispersion can be also very useful for different applications, such as mode laser locking or prism spectroscopy and so on. But it is one of the most challenging that the imaging system are facing, which is defined as the variation of the refractive index as function of the wavelength. And how current method or conventional optics are dealing with such chromatic aberration, they use either a combination of multiple lenses using refractive or diffractive lenses, or using a diplet group lenses in order to compensate this chromatic aberration. But due to the context of miniaturization, we always need to have an ultra thin lens, very flat, tunable, multifunctional at the same time. And recently, metasurface was proposed as an alternative solution to overcome such a limitation. However, current proposed metasurface are seen here. If you look at the bandwidth and the efficiencies that people are providing, it is very challenging to be able to see at the same time high efficiency and broadband at the same time. So now the question was how we can combine high efficiency and broadband meta lens at the same time. To answer to this question, I would like to show what is first the requirement to have a broadband meta lens. To do that, I just consider here a meta lens where we have the substrate and the pillar of the meta lens, and we have R, which defines the position in the meta lens. F capital will be the focal length, and F the frequency. When we have an incident light, in order to focus the light in the red point here, the phase at different position of the lens and the slope at different position of the lens should be different in order to bend light at the focal point. So what I did here is, what we did here is we consider R, which is a position of the lens, and we set the middle of the lens as the reference, and we calculate the phase that we need, which is the phase that we need at different position, which is given by this equation. And if we look at this equation closely, we can see that delta phi is linear to the frequency. So first condition to have a broadband lens, the delta phi, your phase should be linear to the frequency. And this can be done by using a waveguide mode. And the second one is the slope, which will help show the angle that the light is bending at different position of the lens should be also different. So how we can reach these two conditions to be able to be at to have a broadband meta lens, we have to choose a unit cell that have more degree of freedom that we can use to be able to have linear phase shift as respect to the frequency and have a slope, a different slope at different position. So we use this unit cell where we have almost 3 degrees of freedoms. 4, but we will fix the thickness of the structure, and the considered material is titanium dioxide, which is transparent in all visible and in IR. And we use R, L, and W as the physical parameters or as the degree of freedom in order to reach linear phase shift and different slope at different position. So what we first did is we calculate MR, which is the slope, and we start with the unit cell that is unit cell 1, where you don't see any circle, but we have just the radius, which is inside, and the width that we will vary until we reach the limit that we call unit cell 2. How we set the limit here is based on the fabrication requirement. We want to have something that can be done with e-beam lithography, so we fix it at 8. When the width is equal to 80 nanometer, we stop. But if we stop here, we don't have any degree of freedom in order to control the slope again. We decrease the length first, and we add a circle in the middle. And by changing the parameters from 3 to 4, by changing the radius in the middle, we can reach this unit cell 4. And by combining 1 to 4, these 4 different unit cells, we should be able to control both the slope and the phase at different positions in the lens. So this is the proposed structure that we fabricate. This schematic of the fishnet achromatic metal lens. We call it fishnet due to the shape of the structure. So as seen here is the middle in the lens, we have more dielectric, and when we go towards the edge of the lens, we have like a gradient of the structure, which will shape the phase and the slope at the different position. So what we did is we fabricate the structure by using, again, e-beam lithography to define the shape, and using a ALD to do the deposition, and after do liftoff to have the final structure where you have the different shape that is almost looks like exactly to the designed parameters that we propose. So in order to show that this metal lens is achromatic, we first start by looking at discrete wavelengths from 640 to 1.2, which is almost an octave bandwidth. And we look at the focal length in XY axis for the different wavelengths and compare it to the theoretical, which is the airy disk, and we can see it fit very well. And in order to show that our meta lens is achromatic meta lens, what we did is we look at how the focal lengths move as function of Z for different wavelengths. So this is almost 200 measurement for each plot of them. And we look at the focal length here is the black dot that we have here. And if you look at it for different wavelengths, the focal length is almost the same, which means that we have an achromatic meta lens because the focal length is not moving as function of the wavelengths. So to further characterize our structure, we consider different dimensions: a small diameter, 10 by 10, 15 by 15, and 20 by 20. And we look at the focal length as for different resonant frequency and compare it with the theoretical calculation. And you see that the focal length is almost the same, which shows that we have an achromatic meta lens. We also measure the efficiency, which is defined the power at the focal length divided by the transmitted power, and we have an efficiency average of almost 70%. We look at the full half-reach maximum to see if it's diffraction limited, and as seen here also, all three lenses are diffraction limited. So this brings me to the end of my presentation, where I show a topological laser that we can design with different geometrical independent cavities. I show also how we can make an exceptional point in plasmonic system and using it as a nanoscale sensing. And at the end, showing an octave bandwidth achromatic meta lens with efficiency of 70%, which is the highest efficiency so far reported in the literature. So I would like to thank my previous group at UCSD that I was with in the project. And thank you. We'll be happy to take any question.
Thank you.
I'm not sure how to remove to show my video anymore because
Share screen. If you have another monitor, sometimes there's a little control.
No, I just have one. It's okay. Yeah, I think it's good. Yeah, thanks. Sorry if the presentation was cutting since the beginning. I think when I stopped my video, it went better than before. So
we've unfortunately become used to it. It was, yeah, we got very few cutouts actually. We heard most of it. Those are a lot of great, impressive results. Are there any questions? Mike has a question.
Yeah, I have a question. Yeah, very nice talk. I think at the end there you said the diameter of the lens was about 20 microns.
it's very small.
It's very small. So how can you focus optical light with such a small diameter? The diffraction of the aperture itself is going to prevent tight focusing.
The diffraction of, if you have a pinhole right before the meta lens, you can avoid having any other light going on. You can, for example, have a pinhole that have a size of 40 microns, that is the double of the size. And if you pass through, because all the lens is transparent, is the titanium dioxide. So if you have white light source passing through, he will pass, only the light passing through the lens will be focused, but the other light will go. Oh,
okay, that's right. Can you say again what's the focal length and then what's the focal spot size?
The focal length was the 0.1, 0.2. The maximum was 0.2.
Of what units?
The focal length?
Focal length.
Oh,
length.
Let me just go back.
I missed that number. I mean, it must be very short.
Yeah, it's very short. I think it was 50 micron or
okay.
Yes,
that's a difference. Yeah, the different scale than we're usually used to.
Exactly, it's a very small size. Yeah.
Okay, thank you.
There's a numerical aperture that is around.
You shouldn't call it a micro lens. Call it a nano lens.
Exactly. But now the what people are trying to do is, because the challenge in metasurface is when you increase the size, that means you need more phase when you are very far to the center. So you have to need more parameters to bend the light. So increasing the size, you can go up to 100 micron to 100 micron. But if you want to make it a centimeter size, it is very challenging because you will not have enough phase to bend the light back.
But you can make a Fresnel zone lens.
Yes, you can make final zone lens.
Nice.
Jason.
Yeah, thanks. Thanks for the great talk. So I had two questions. One's from the first third of the talk. Could you tell us a little more about the mechanism for how the light is aware of the magnetic field? So it must have to do with the electrons in the material somehow. But what's the exact?
You have, when you have this magnetic material, you have the tensor for the permittivity. For example, when we design it, we just change the tensor of the permittivity to be able to have it. And when we do apply a magnetic field, we have like a coil that we have our sample in the side, in the middle, and we apply magnetic field that will flip directly the sign or change the permittivity that will break the symmetry. It is more based.
And so what size of changes can you get with this kind of mechanism? I'm just can you make giant changes in permeability this way?
No, it will not be a giant change. The change in the permittivity is very low. I cannot give an exact number, but it's very low. Yeah.
But it's enough to.
It's enough to break the time reversal symmetry.
Break the symmetry.
Yeah.
Thanks. And sorry if you don't mind. I also had a question about the second part on the for the exceptional points. You mentioned this sensitivity boost that comes from it being non-analytic, having some power other than one.
Yes. Mm-hmm.
So is there an easy way to think about how to change that power? Like, is it related to some kind of symmetry or dimensionality of your?
How to increase the sensitivity?
Sorry?
If I understand clear your question, is how to increase the sensitivity?
I was wondering if you knew of ways to change that exponent. So you showed a square root singularity at the exceptional point.
Yes.
Is there a straightforward way to think of a 1/3 singularity?
You can have, is what I saw in the when you have exceptional point at second order is square root. But if you have order of n, which means that you have n modes that you reach exceptional point, your n will increase n times, like square root. You have a n root behavior of your sensitivity.
So it's the number of degrees of freedom that kind of.
No, it's the number of modes that will reach exceptional point at the same time. If you have two modes that have resonance crossing,
control more modes, you can change that exponent.
Exactly. If you increase the number of modes that reach exceptional point that have loss and resonant frequency at the same time, you can increase the sensitivity.
I see. Yeah. Thanks.
But in these two layers, it will be very difficult to have another mode that can have the same behavior. We can increase the number of the layers to think about having it. But in this current configuration, we cannot.
Okay, thank you.
Yeah, no problem.
Well, I had a question about the commercial opportunities here. So, so you've got the numerical aperture for the meta lens, for example, is something that is reasonable for a camera.
Yes.
What size would be needed to make, like, a billion of these and put them in the next iPhone?
So let me maybe answer in different way. For example, if you want to have highest numerical aperture and largest lens, there is always a trade-off. You can increase the size of your lens, but you have to decrease the bandwidth and increase the numerical aperture. In this case, you don't need to have multiple lenses at the same time. But as you ask now, you can have 10 micron by 10 micron size of lenses that you can put multiple together, like a micro lens that people used to before, and use it. I'm not sure if I answer correctly your question.
Yeah, and I had another question too. So is this fairly insensitive to the polarization of the light? Like I can imagine.
Yeah.
Okay.
Yeah, because we use the cylindrical shape. If you want to have only like one polarization, you can use rectangle, or we can also design it to have to accept only circular polarization by using geometrical phase. But here is linear polarization, and since the shape is circular, is you can use X and Y polarization. Both of is insensitive to the polarization. Yeah.
Let's see. Do we have any other questions from the audience? It's getting to be late on the East Coast, and we've had a lot of filled Zoom sessions today. So thank you very much for you're a very busy professor right now, I imagine. So
No
thanks for
problem.
taking some.
It's my pleasure to be here.
Great. Well, let's thank Abdoulaye again, Professor Ndao.
Thank you.
Great. And yeah, I look forward to continued conversations.
Okay.
Thanks, everyone. And sorry for the Zoom arrangement. I know that's frustrating.
It's okay. It's the Zoom. Sometimes you don't understand and you cannot control. So it's okay. I'm sorry for you guys if sometimes it's cut or you don't like hear what I'm talking about. But
Well,
hopefully one day we will have chance. So I will come to present physically.
Yeah.
That will be more interesting than Zoom. But yeah.
Well, thanks also for being so responsive. Like we've had some cases where where the speaker didn't catch so quickly that they were talking to a blank screen or something, and you were quick to respond. So thanks.
No problem.
Thank you very much. It was a great talk.
Thank you. Thank you for being here. Thank you.
Well, I wish we could take you out to dinner, so it'll have to wait for a real visit. Okay.
Okay.
Well, yeah, I'll be in touch about the meeting next week, and
Okay.
I'll confirm. Brian Smith indicated he wanted to meet with you tomorrow, and I'll just confirm that time.
No problem. Just let me know. I will be ready to discuss with him, and I will prepare the slide for the project that I would like to have for FIB. And whenever you have time that you would like to discuss, let me know so we can discuss it.
Sounds great.
Yeah.
Cool. Well, thanks again.
Thanks. Thank you. Have a good night and talk to you soon.
Sounds good. Bye.